Hello everyone, welcome to Lecture 5. In today's lecture, we will be talking about everyone's favorite buzzword, machine learning. And this will be a general introduction to machine learning as well as linear regression, which is a type of machine learning that you will implement yourself. So here's the plan for today. I will first talk about what machine learning is, why do we use it, and the different type of machine learning problems and models that you might encounter. Then Tanu will take over and she will talk a bit about linear regression, which will be a first machine learning model. And it's a really useful model to implement. And then we will be showing a demo of linear regression on an actual data set. So in order to start thinking about machine learning, we need to think about both the machine part of it as well as the learning part of it. So that necessitates thinking about what computers do well and what computers can't do so well, but humans can. So here's some things that computers do fairly well, but are difficult for humans to do. So computers can repeatedly follow a certain set of instructions without making an error. So if you told me to multiply something by 2 1,000 times, I would probably mess up somewhere along the way, out of fatigue or just because I can't focus. But a computer does not run into that problem. A computer can do it as many times as you tell it to without an error. And computers also really good at performing complex arithmetic calculations. So if you ask me to, I don't know, give you the fifth root of 27, I'd probably struggle with that, but a computer can do it fairly quickly. And computers are also great at performing transformations on data. So you did that, you did that by yourself in the first two assignments, as well as saw it in the first two lectures using pandas. So that is another thing that computers are really good for. And computers can also find numerical patterns in quantitative data. So an example of this would be calculating how related two variables are, or how much does a change in one variable influence the other variable. And this is something called correlation. If you haven't heard that before, we will be talking about it really soon. And another way that computers help illustrate patterns is by plotting figures, such as graphs, that allow humans to clearly visualize the trend in data. But computers can't do everything, and they certainly can't do a few things that humans find fairly intuitive. So computers can't think of different ways to solve problems. So computers are constrained by their code. They cannot do anything that's outside their code. But humans can think of various different ways to solve problems. And humans are also responsible for coming up with a set of repeatable instructions, also called algorithms, that computers can use to solve problems. So computers can only follow these instructions, but they cannot come up with it themselves. Well, at least not yet. And computers cannot gain any deeper intuition about data. So we know that let's say a data set has an animal column and it has an entry of cat, we know what real world object that corresponds to, namely a cat. But a computer just sees a bunch of characters. It doesn't have any deeper understanding of what it means to be a cat. Okay, that was quite philosophical, but machine learning unites the two approaches. So what we aim to do is we aim to leverage the strengths of both what computers can do well as well as what humans can do well. So the primary motivation behind machine learning is actually similar to how humans learn as infants. So we find patterns in our surroundings, we experiment with different responses. So for example, a pattern that I might find is that, well, there's tea served at every day in the evening. And the different response I could try out when I'm an infant is I could try putting my finger in a cup of hot tea, which would not really end well because I will feel pain and I'll withdraw my finger away. So that goes on to a third point, which is the repetition of a certain stimulus and response hardwire a course of action. So what this basically means is that I put my finger, it's hot, the my nerves send an impulse to my brain telling me to feel pain, and I withdraw my finger. So machine learning essentially tries to mimic this process in computers, and systems can learn without explicitly being programmed. So when I put my finger in the boiling hot cup of tea, I don't explicitly tell my finger to move out because I feel pain. That pain instinctively tells me that, okay, this is a bad idea. So we aim to do something quite similar with computers. So we tell a computer that, okay, here's something that you want to minimize. And if you're maximizing this, then that's the wrong direction. You do not want to do that. Just like I do not want to put my finger in a cup of tea. And again, so just to repeat, we do this in order to leverage the strengths of computation as well as human learning. And um, a kind of um, a kind of thing to keep in mind with machine learning is that computers can only understand numbers. So whatever observations we may have, we need to convert it into quantitative data. So computers don't necessarily do well with qualitative data because computers in and of themselves are fundamentally like made up of ones and zeros, and they can only understand numbers. So we need to find a way of converting um, what data we have, if it is qualitative, into quantitative. A way of doing that would be, for example, if you see an image, then we can convert it into pixel values that we can pass to a computer that can find patterns in those pixel values. That's a nice segue to an example of machine learning. So this is a fairly simple machine learning application. So it essentially, it looks at the picture and it tells us whether the picture has a dog in it or something that's not a dog. And over here, you can see that it flags this dog at this picture as having a dog in it, and it flags this picture as not having a dog in it, which seems very accurate. So let's think about how a human would actually go about solving it, because it is fairly intuitive for all of us. So we all have a sort of background knowledge of the world from when we are infants. We know that a dog has four legs. We can recognize its head, its ears, its tail, and we also know that dogs don't usually have wings. So all of this tells us that the picture on the left is likely to be a dog, and the picture on the right is probably not a dog. But a computer doesn't really have this real world intuition, does it? It doesn't know what being a dog is. It cannot know or recognize anything by itself. So, how do we tell a computer to recognize if an image is a dog or not? So, the way we do this is there are two approaches. And the first one is that we can explicitly program the computer to recognize certain characteristics as being a dog. So, for example, we know that dogs have ears, noses, and four legs, let's say. And we can program the computer to tell us that for anything that does not have ears, noses, and four legs, to return that it's not a dog. So this would work in the case of the bird because it sees that it only has two legs, so it's probably not a dog. Um, yeah, and it seems like a good idea because we don't really need any data. For this, we just need to know a specific set of rules about what it means to be a dog. But there's a problem. Over here, we see a picture of a dog, but we can only see three legs, right? And I mean, if a human would look at this, then it's pretty obvious that this is indeed a picture of a dog. But a computer can only see these three legs. As humans, we might gain an intuition that there's a fourth leg behind the dog's body, but over here, the computer can only see these three legs. And as a result, it would not comply with the rules, and the computer would say that this is not a dog, which is an inaccurate prediction. So instead, what we want to do is, instead of like defining explicit rules that define what a dog is or what a dog isn't, we want the computer to build by itself a collection of factors that we associate with a dog. And another reason why we might not want to have a set of rules is that it is very, very difficult to manually encode all of the factors that constitute being a dog. I mean, just think about the various types of dogs there are and like the number of characteristics you may find of a dog. So you can say that a dog does not have does not have, I'm sorry, does not have wings, and um, a dog does not have a horn, let's say. So there are just infinitely many characteristics that you can find, and it's really difficult to come up with a set of comprehensive rules that summarize what being a dog is. So what do? We automate this process of coming up with criteria and learning. And that is the essence of machine learning. So this leads us to a second approach, which is training the computer with lots of data. In this case, the data would be pictures of dogs. And we can also label these pictures in order to tell the computer whether the picture that it sees is a dog or not a dog. Again, computers do not understand qualitative data, such as not dog or dog, because it doesn't know what it means to be a dog. So we need to convert it into some kind of quantitative data. So over here, an example would be the label of 0 if it's not a dog, and the label of 1 if it is a dog. And the computer goes through all these images. There could be thousands, there could be millions of images of dogs, and it recognizes certain characteristics of dogs by comparing all the images that have the label of 1. corresponding to it. So because all these images have something in common that resembles what it is to be a dog. And while we may not explicitly know all these rules beforehand, the computer can do a good job figuring it out. So for example, it could, yeah, just going back to this, a computer can only recognize quantitative data. And over here, it could be something like pixel values of the image. So it could see a set of pixel values that are in common of all the dogs. And this would be what we identify as a tail. But a computer doesn't know that. A computer just knows that this set of pixel values corresponds to a greater likelihood of it being a dog. So that is a rule that it can implement by itself. But notice it does not have a deeper understanding of what a tail is, but it still can classify it fairly accurately um, because all tails will have the same set of pixel values or something very similar to it. And a good thing about this approach is that we do not need to explicitly program. So while in the previous approach, we needed to come up with rules and decide what a computer would do if it met the rules, if it didn't meet the rules. Over here, we only need to know we only need to have a ton of images to feed the computer. And we don't need to know exactly what the characteristics of a dog are. The computer comes up with those by itself. And after it comes up with those criteria, it outputs one, that is a dog, if the certain criteria are met, and zero if they are not. And you might ask which one is better, and truth to be told, they're both good in their own ways. So in approach one, we do not need to feed in any data to train a machine. So this would be nice when there's not a lot of data available. I mean, there are millions of pictures of dogs, but for something that may not necessarily have that much data available, it probably makes sense to come up with a set of rules that describe what you're looking for. And as a result of not feeding in any data, it saves a lot of space and computational power. And the only reason explicit programming was possible in this case was because we knew dogs have four legs, no wings, etc. But again, as we saw in this example, this does not always work, right? Because this is an example that is a dog, but the computer does not see four legs; it only sees three. And approach two is the machine learning approach, where the learning is automated. So the whole process of coming up with characteristics that describe the object is automated, and a computer does not need the domain knowledge. So a computer does not need to know what exactly a dog is or what exactly a tail is. It just needs to know that this set of pixel values increases the likelihood of it being a dog. And here's a few terms that will prop up quite frequently during when you learn about machine learning, as well as today's lecture. So the first term is training data. So this is essentially the set of pictures that we feed into the model that trains it to identify whether an image is a dog or not. So it is the data used to train your machine to eventually figure out a repeating pattern. So over here, it's a picture of dogs. And then the testing data is the data that we test the accuracy of the model on, because we do not want a model that perfectly predicts all the things that it has seen, but doesn't do well with stuff that it hasn't seen before. So we see that we see if we're getting predictions that we wanted when by using the testing data on data, which is essentially data that we have seen before. And the next thing is features. So features are characteristics or the phenomenon we are observing or modeling upon which the machine bases its prediction. So it's very analogous to variables. So over here, features with a dog could be like the number of legs it has. So if a dog has four legs, then then the likelihood of it being a dog increases. And labels are labels that we provide training data. So over here, 0 for not dog and 1 for dog are examples of labels. And accuracy is a fraction of predictions that we get, that the model gets right. So if we have testing data and the model gets like 9 out of 10 of those images right, then we'll say it has an accuracy of 90%. Okay, so in machine learning, there are two main types of learning. So that is what we call supervised learning, and then there is unsupervised learning. So supervised learning is further divided into classification and regression. So we will be implementing a regression model later in this lecture. And there are a bunch of other models which you will get to later. And supervised learning is Essentially, we provide a set of labels with training data. So we tell the computer what is right and what is not. So over here, we have, in the previous example, we had 0 for not a dog and 1 for dog. So we say that 0 is not right, while 1 is right. Or we can also have something like sales prices for houses, in which we say that a house with this number of bedrooms, which would say this price, would probably sell for a certain price. And the model would learn the relationship between the data and labels. So it would observe patterns and it can make predictions based on those patterns. And the way that the supervised learning model makes its predictions is that when it's given data that doesn't have an explicit label, it can weigh those characteristics according to the set of rules that it comes up with, and it can provide a close estimate for the label if we implement a good model. Unsupervised learning is different because the training data for this model does not have labels. So we don't say that this image is a dog or this image is not a dog. It is a model's job to figure that out. It's a model's job to find structure in data. So the data we're feeding it is going to be unstructured. And it needs to find something like different groups in the data and label them and tell us what it is. So an example of this would be feeding it billions of images, and it tells us it groups the images which have dogs together, and those that don't have dogs in a different group. And another example would be we can feed a ton of dog pictures, and then an unsupervised learning model can group these dog pictures according to different breeds. Okay, so now we will be talking a bit about supervised learning because regression, the algorithm that we will be implementing, is actually a form of supervised learning. And the other main form of supervised learning is something called classification. So classification is very similar to what we did with the dog and the not dog example. So these are used for categorical predictions. So again, a categorical data type is a data type where there can only be a certain set of possible values. So in the case of dog or not, we only have two possible values. So we have either 0, that is not a dog, or 1, that is a dog. And again, we cannot have any intermediate values. We cannot have a zero point 0.5 value over here because that doesn't make sense. You can't have zero point 0.5 of a dog. And yeah, and the second main algorithm that we'll be looking at is regression. And regression is used for predictions based on continuous data. So over here, there can be an infinite set of possible values. So let's say we have a model that predicts housing prices based on certain characteristics, such as the number of bedrooms and the listed price, and so on. And it can return any positive number or 0, well, hopefully not 0, but any positive number as the price. And intermediate values are possible in this case. So if you have two prices as 250 and 251, which I just realized are quite low for houses, but let's go with it, then we can also have a price of 250.5. So that is perfectly valid. And this is also very analogous to discrete and continuous data. So regression would be used for continuous data, and classification would be used for discrete data. And another example of this would be that regression is predicting what the temperature is going to be tomorrow. So over here, the prediction would be 84 degrees, but we can have any possible set values. We can have something like 70 degrees. We can have something like 84.2 degrees. We can have 90 degrees. We can have any possible value in this particular range. With classification, and on the other hand, we have only two possible values. We either have cold or we have hot. There is no real intermediate value over here. There's no warm or mild. It's just cold or it's hot. So there are only two possible outputs over here, while over here there are infinitely many possible outputs. And I will hand it over to Tanu now, who will introduce linear regression, which would be the first machine learning model that you'll implement.
Hey y'all. I am your TA for today. My name is Tanu. I am a junior majoring in computer science and gender and women's studies. I'm going to be talking about linear regression, and let's get right to it. So linear regression is going to be your first ML model. And what linear regression basically is, it's a way to model the relationship between two variables. One, which is the dependent variable, like the name suggests, it depends upon the values that the other variable takes on, the explanatory variable, um, to get its own value. So its own value depends upon the value of the other variable, and we try to find a way to mathematically model this relationship between these two variables. So that's what linear regression is all about. Um, and so let's just say we have this scatter plot, right, with a bunch of data points, like if the value of x here is 15, then the value of y over here is, I guess, 92 or something like that. So that's how each one of these scatter points are in the scatter plot. And if we were to vaguely try to find a relationship between them, we'd say that a straight line going downward would be a good estimate of the relationship between them, right? And that's linear regression, just finding a line that best fits a model that has somewhat of a linear behavior going on. And what I mean by linear behavior is that we can use a line of the form y equals beta 0 plus beta 1 times x to model our data. And this is just a simple line form equation that you probably learned in high school. And we fit this line to a scatter plot that has a bunch of data that's scattered around but can be modeled using a line, right? And that is pretty much what linear regression is. Um, Again, to variables and the relationship between them. So I hope by now you understand what linear regression is. So now that we have a basic idea of what it is, let's get into the more mathematical part of it, right? And so there are four important mathematical things about linear regression. The first one is correlation of data. And I'm going to go more in depth into each one of these. But yeah, the first one is correlation of data. The next one is the slope. Then we have the intercept. And the fourth one is y equals slope times x plus intercept, which is the line equation that you're probably familiar from the SATs or something like that. Yeah, so correlation is, we use the mathematical term correlation coefficient or R to measure the degree of correlation or the degree in which two variables are dependent, right? So it's always in between -1 and 1. And 1 refers to a perfectly positive linear relationship. What this would mean is that a straight line of slope 1 goes through each one of the scattered points and perfectly fits the data that we have, right? And -1 just means like a negative relationship, a slope that goes downward. And each one of the points in the scatter plot is perfectly fit by that line. And so this first graph is that of a positive correlation. This just means, like you can see, a line with a positive slope or a line going upwards is the relationship going on between these scatter points, right? In the second graph, we have a negative correlation, like the first scatter plot that I showed you. This also goes downward. Vaguely, all the points converge to a lower value. As the value of x increases, the value of y decreases. And the last one is just a correlation of 0. What 0 means is the slope is 0 and there's, there's no correlation between them. We can see that the points are just randomly scattered across the graph. There isn't any pattern to them as in the first or the second graph. So this is the first mathematical formula, and this is for correlation, which is R. And I know it looks a little um, too much, but it's actually not that bad of a formula. And we usually use libraries to get these values anyway. But it's important to know how to do them mathematically. So what n in this equation means is the number of data points that we have. X corresponds to one particular X value and Y is one particular Y value. And this giant E is sigma, which means the sum. So the sum of each of the XY values is what this, the product of the XY values is what this means. So let's say we have X values 1, 2, 3, and Y values 1, 2, 3. Sigma XY would mean 1 times 1, X equals 1 times Y equals 1, which is 1, plus X equals 2 times Y equals 2, which equals 4, and then X equals 3 times Y equals 3, which equals 9, and then we add all of this, and that's 14. So that's what sigma is, and that's what X and Y correspond to, each one of the X and Y values. And in the example that I just gave you would be 3. And we just have to plug in these values again for sigma X, sigma Y. So the sum of all the X values times the sum of all the Y values is subtracted from this, and that's divided by the square root of n, which is the number of data points, times the sum of all the values of X squared subtracted by the sum of all the X values, and that, and we take the square of that. So what's the difference between these two is that here we're taking the sum of each one of the X squared values, and here we're taking the sum of all the X values, and then we square that. So it's a little nuanced. And we multiply that with this, where we're doing essentially the same thing, but just with Y. So n, again, the number of data points, times the sum of all the Y squared values subtracted by the square of all the of the sum of the Y values. Yeah, and then the next one that I said was we'd be doing slope, and slope is just the rise by the run, and I'd hope that a lot of you are probably familiar with this. And it's the equation that we use in lines. So let's say there are 2 points on the line, x1, y1, and then x2, y2. The slope would be the difference in the y values, so y2 minus y1, divided by the difference in the x values, uh, which is y2 minus y1. So this is the rise, right? The difference in the y values. And we divide that by the run, which is the difference in the x values. And the last thing that we needed was calculating the intercept. And to do that, we have this line equation where y equals slope, which we calculated here, right, times x plus the intercept. And the y-intercept is this value, which is the value where the line intersects with the y-axis. So the value of y when x equals 0, that's the y-intercept. This point right here is the y-intercept. Okay, so we have this line equation, and to calculate the intercept, all we have to do is we know the y value. We can just take some y value. We know the slope. We know how to calculate the slope. We can take some x value for that y value. So these have to be of the same pair, right? So over here, there's x1, y1. You can take both of them as the x and y values, but you can't take x1 and y2. That's not allowed, right? And so we take two, a pair of x and y values, right? Y equals slope times x plus the intercept. And because we have all these three values, we can substitute that in this equation and find the value of the intercept. And what do these describe? The the slope describes the average rate of change. So what that means is the amount that y changes given that given that x changes by just 1 unit, and 1 unit just means a standard unit. So given that x changes by 1 centimeter or 1 kg or something like that. Given that x changes by this one particular standard amount, what's the change in y? That's what the slope represents, right? The average unit of change in y for every unit of change in x. And the intercept, like we talked, is the y value when x is 0. And there are two types of linear regression. What we've been studying till now, and the examples that I've been giving you are of simple regression. And so it's just a straight line fitting a scatter plot. Okay, let's do a quick quiz. Do this in your head, so that you have a mental check to see if you understand this. What type of a correlation does this graph have? Okay, and I'm gonna wait 5 seconds before I answer the question. It's probably been 5 seconds now. So yeah, if you thought of this having a positive correlation, you're right. This is an upward line, right? It has a positive slope. The slope's increasing, or the value of y is increasing as the value of x increases. So yeah, that shows that it has a positive correlation. And yeah, it's this line equation that we talked about that models this. So previously in the equations that I showed you, we did have a y, we did have a b0, beta 0, which is the y-intercept, and we did have beta 1, which is the slope, and x. But what is this e, this new e that we have? And this is just the error, right? So what error means, like you can see, these data points aren't exactly modeled by our line equation, right? Like a lot of them stray away from it. And this line is just an approximation of where these values would be. And that's what E is. E measures how much, or measures the degree by which these data points stray away from the actual line that models them. And if we had um, a correlation value of 1, and if the slope were increasing like this, each one of these scatter points would be exactly on this line. And so we'd have an error of 0. So that's what all of that is. And that's simple regression. And then the next thing that we have is multiple regression. And that's, we again model it linearly, right? but we have multiple factors that affect this y value. And so we use this equation where y is the dependent variable, the one that we want, and x1 is the explanatory variable. And the other things are coefficients, right? And e is the error, and beta 1 is the slope, and we use this equation to model it. And yeah, that's multiple linear regression. In our examples, we'll just be going through simple linear regression, and knowing that and properly understanding and how to implement that would make it very easier to just have the same mathematical concepts to apply that to multiple linear regression. And I talked a little bit about this already, but we need to minimize the error, right? There's no point of having a line that's just so far off from all of your data points, and there's just, yeah, what's the use of having a model then? You want the model to be as close as possible to the values or to the data set that you have. And that's why we need to minimize error. So this graph, these colored lines that we see are the degree by which, so this point, let's say this is the point, this is the actual data point that we have, and this is how much the graph, the line that we found right now strays away from this data point. So this is another data point that we have, and this is the degree by which this strays away, this line strays away from this data point. And that's what each one of these are. And the lesser this value is, so this, we see that over here, there's just a value of 1. We want that, right? We want it to be as small as possible for all the data points that we have. So we need to minimize error. And what we need to minimize is the sum of all these errors, right? Like just not for one data point, but the sum of all these gives us the thing. Okay. And the last thing that I want to talk about is the fact that correlation is not causation, right? So let's say we model two things on the x and y axis, and we find a way, we find a line or a trend in between them. We were able to get a good correlation, a strong correlation between two data points, between two variables. That doesn't mean that there is some reason behind it. That doesn't mean that there's there's a reason or there's a cause why this relationship exists. And here's an example. The sales of ice cream and sunglasses are strongly related, right? But that's not because there's a relationship between them, but it's just because they're affected by the same season. And this is just a cautionary note that correlation doesn't always mean causation. And now my partner Siddhant is going to take over, and he's going to introduce he's going to introduce you a little bit to these machine learning libraries. But that's all for me for today. Thank you so much, and I'll see you all next time. Bye bye. I'll have to stop this.
Hi, so this is just going to be a quick demo of how to use linear regression on an actual data set. So we start off, as always, by importing all the packages we'll need. So we have NumPy, we have Pandas, we have Matplotlib, and we have the two packages that we talked about in lecture. So we have from scikit-learn, we have train test split, which, just as a reminder, splits the data into the training data and the testing data. So we train a model on the training data and use the testing data in order to validate our predictions. And we also import the linear regression module from scikit-learn. That essentially is a module that helps us implement linear regression without having to do too much work. And the next thing we do is to read data from a particular file. So over here, I have it stored in an Excel file, and I will read that and store it in a pandas data frame. And over here, you can see that there are two columns. There's a male unemployment, there's female unemployment, and there's 13 rows. And over here, we notice that this is a data set containing the male and female unemployment rates in 13 cities. And let's say that we want to predict the female unemployment rate given the male unemployment rate for a given city. So here the predictive variable, that is our x, would be the male unemployment rate, and the response variable, our y, would be the female unemployment rate. And something that we often want to do is something called normalization. That is you convert all the variables that you have to a common scale. And we do this so that the regression model is more effective and more accurate, because you can imagine a scenario in which, let's say, you are trying to predict the housing prices and you have various criteria. So you probably look at a number of bedrooms that can range from 0 to 5, although you probably don't want a 0 bedroom house, but so 1 to 5. While you can have the listing price range in like the thousands of dollars. So just by the virtue of one of the list price being several orders of magnitude higher than the number of bedrooms, it can have a disproportionate effect on the model that we choose to implement. So in order to avoid that, we do something called normalization, which over here consists of subtracting the mean of each column and then dividing it by the standard deviation. So over here, we don't really need to do it because the variables are all in a similar scale, but it's a good idea to do nonetheless. So over here, we can see that they're pretty much in the same scale. So the male unemployment is normalized from minus 1.78 to, it looks like, 2.2, and the female unemployment rate is on a similar scale. So that's good. And the next thing we want to do is splitting the data into training and testing data set. So over here, we use train test split. That is the module we imported from scikit-learn. And over here, we're passing in the normalized data frame as the first parameter. And let's say I want my testing data set to be 15% of the normalized data frame. So I want it to be 15% of 13 as the size of the testing data. And basically the random state is something that helps maintain consistency when we call train test split multiple times. So let's say that this picks out options 4 and 7, or rather rows 4 and 7 as my testing data set. And that corresponds with the random state of 42. But the next time, if I run it with a different random state, let's say I have a random state of 37, it may not necessarily pick 4 and 7. It may pick something like 1 and 10, which we don't really want if we want to maintain consistency. So that's why we use a set random state in all the times we're calling train test split. Over here, we only call it one, so it shouldn't be much of a difference, but it's always a good thing to do. And let's see the shape of our training data set and of our test data set. So the training data set seems to have 11 rows. So it would be 10 out of these, I mean, sorry, 11 out of these 13. And the testing data set would have 2 rows. And something that we might want to do is just quickly visualize the data so that we can see if linear regression is something that we might want to do. So the reason that this is quite easy to do over here is because we only have 2 variables that we want to predict. That's kind of the reason I chose this data set, because it's easy to visualize. But in practice, you'll often have a lot more, and it might be a bit difficult to visualize it accurately. But over here, we only have 2 columns, so it's quite easy to do. And over here, we notice that the female unemployment generally rises when the male unemployment rises. So over here, we notice that a linear relationship might describe this pretty accurately. There might be a high correlation coefficient between the 2 variables. And therefore, the linear regression seems like a good idea. And once we decide that we want to do linear regression, we can allocate names to the predictor and response variables. So again, just as a reminder, X is the predictor, Y is the response, and we want to predict female unemployment given male unemployment. So X would be male unemployment, which is the predictor, and Y would be female unemployment, which is the response. And over here, we assign X to the train of unemployment male, Y to train of unemployment female, because X is the predictor and Y is the response variable. And we do a similar thing for test. Now, the first thing we'd like to do is run linear regression manually. And the way that this works is that we take any arbitrary straight line. It may not pass through all the data points. It may not describe it should not describe the relationship perfectly. If it does, it'll be a massive fluke. And at each iteration within the model, you want to push that particular line so that it's closer to describing the best fit line or the line that best describes the linear relationship between the two variables. And the best fit line also corresponds to the line with the least root mean square error. And if you remember from lecture, this is the goal of linear regression, is to minimize the root mean square error. So a line that minimizes the root mean square error describes the trend in the variables. This describes it, describes it most perfectly. Yeah, most perfectly. Okay, we'll go with that. And just as a piece of terminology, I might use the term cost function, and over here in this example, it is interchangeable with the root mean square error. So if I say minimizes the cost function, it can interpret it as minimizing the root mean square error, which is again, just getting to the best fit line. And I have defined a few functions in this Jupyter notebook that will help us implement linear regression from scratch. You don't have to worry too much about it now. You will do a very similar thing in the assignment, but as a result of that, I'm not going to show my code for that. We just need to know that I've defined a function called run linear regression, which takes in a parameter n, and n is simply the number of times we want to run linear regression, or the number of iterations. Or basically, at each iteration, we push an arbitrary straight line closer and closer and closer to describing the best fit line that corresponds to our variables. And yeah, so I will just stop sharing my screen and run that real quick. Okay, so I have run that. And now let's see what happens when I want to run linear regression. Let's say I want to run it once. And if you look at the second graph, you can see that it's almost a line parallel to the x-axis. It's not quite. It's pushed up a tiny bit towards describing the line that describes variables. So we'd ideally assume that it'll be a line something like this, that describes the relationship between two variables. And this is not exactly a line parallel to the x-axis, so it's pushed a little bit towards it, but it's nowhere near describing the relationship between our data. And let's see what happens when we run it, let's say 5 times. Okay, so now we see something interesting. We see that there's this convergence graph of cost function, and it seems to be that the cost is decreasing with the number of iterations. Just a reminder, the cost is simply the root mean square error. So the root mean square error was decreasing when we increase the number of iterations. So over here at the 5th iteration, we have this line, and this line describes the linear relationship between the variables a little bit better than a previous line with just one iteration, and definitely a lot better than just a line passing through a parallel to the x-axis. But it's still not great, is it? Let's see what happens when we run it, let's say 15 times. Okay, now we begin to get somewhere. We see that it's getting closer and closer and closer. The cost function is continues to decrease. Let's say 50 times. Okay, now it looks very good. Now it looks like we are getting an actual regression line that describes a variable. And we also see that the cost function is still decreasing, but it's begun to stabilize. So it's begun to approach an asymptote. And that is our goal. So for those of you who may be familiar with calculus, what we want to do is we want to minimize the cost function, or find the minima of the cost function. And let's run linear regression 100 times. And over here, you can see that it's fairly good, best fit line, as well as you can see that the convergence graph has almost reached an asymptote. So let's just run it 200 times just to be very, very sure. And over here, you can see that it's flattened out considerably. And this is actually a fairly good regression line that seems to describe the trend between our variables. Okay, fantastic. Now, that actually was a lot of work for manual regression. And luckily for us, there's an external data science library called scikit-learn that makes it a lot easier. So what we need to know, and this is just a recap from lecture, is that linear regression creates a new regressor object that we can fit to a particular set of predictor and response variables by calling the function .fit. So here LR is a linear regressor that we create by calling linear regression, and we fit it to our training data, that is X and Y, and store the result in model. And then we can find the coefficients of model and the intercepts of model. And another thing to notice about the manual implementation of linear regression is that we have two optimal parameters, and these optimal parameters correspond to the slope and the intercept. So I believe the second term over here is the slope and the first term is the intercept. So it will correspond to the y is equal to mx plus c. This would be m, and this would be c. Fantastic. And we should get a similar thing over here. So over here we get an array that is 0, we can ignore that. And then we can see that this is the slope and this would be the interceptor. And if we plot it out, I've created a function called AB line that just plots it out. That just plots out the line. You can see a graph that looks very, very similar to what we had over here, which is quite cool that the external data science library seems to do exactly what we just did. And if we predict values in our training set, we notice that these tend to be very similar. So we have a fairly negative value over here, we have a fairly negative value over here, we have a very small positive value over here, we have a fairly small negative value over here, moderately positive, and it goes on. So it seems to be doing a fairly good job. And if we want to compare a slope and intercept with the manual approach as well as scikit, you can see that we've gotten very, very close. I mean, this is 0.17558, 0.17558, 0.8554, 0.8555. I mean, we're accurate up to the 4 decimal place, which is quite cool. Yeah, so that is a demo of how linear regression is used on an actual data set and how we can use it to fit a regression line between two variables and how we can use it to model the relationship between a particular pair of data.